Alright people, welcome back. So in today's episode we are continuing our series of exercises on dynamic programming, and today we're dealing with 120 triangle. So to be honest, I already had a look at this exercise and it feels again the repetition of the same stuff we're doing again and again with dynamic programming. So given a triangle array, return the minimum path sum from top to bottom. So first, let's define a triangle array. So here, for example, you can see an array, and you can see each time you add a new element, like the length increases by 1, so that you can imagine this grid as a triangle, okay? And for each step, you may move to an adjacent number on the row below. So more formally, if you are on index I on the current row, you may move either to index I or to index I plus 1 on the next row. So basically, we're here at 2, and then we can move to 3 or to 4. Now, let's say that we moved to 4. Now we can move either to 5 or to 7. And then let's say that we move to 5, we can move either to 1 or to 8. Okay, so the best path, of course, would be 2 plus 3 plus 5 plus 1, because this is the minimum sum. Now the question is, how do we find the minimum sum? So here is my idea. Again, the same thing that we did before, literally. We can just say, okay, for each element, we find the minimum path that brings to that element, and then we simply take the minimum of all the minimum paths in this last row, so that we start at 2. Of course, the minimum path is 2. Then, for each element of the row, we calculate the minimum path. So this is gonna be 5 or 6. Then for each element, we calculate the minimum path. And for the way we do that is basically saying the number. So for example, this 6 plus the one above it. So the minimum between nothing and 3. So this is gonna be 2 plus 3 plus 6. So this is gonna be 11. So for 5 instead, is gonna be 5 plus the minimum between the path that brings to 3 and the path that brings to 4. And for 7 is gonna be 7 plus the minimum path that brings to 4, and so on and so forth. Okay, the only point is this theoretically works, but I'm not sure how to code it. So let's try to understand. So of course, we have this triangle, and we can do something let's say, so the first, of course, the first minimum path is actually equal to the value itself. So we want to start, let's say, we have a triangle length. Okay, so let's say something like that. We know that the length of the triangle, let's call it n, and then we do something for I in range 1n. Okay, because we want to skip the first value, which is not needed actually, because it's already there. And so we're triangle. So we're okay, let me think. So we can do something for j in range, and then we can use the length of triangle I, so that we're basically extracting, let's say in this case we extract 3, 4. And now for j in range, so basically we have 0 and we have 1 because the length is 2. Yes. So for what I do is to basically take triangle I, j, and the real, the new value must be the minimum sum that got to that value. So this is gonna be this is going to be triangle ij, of course, plus the minimum between triangle, actually let me use j and I, because that refers to what used in here. So let me just say ji here. So I just invert to be consistent with the notation used by the exercise. So for range in length triangle j, so triangle ji is equal to triangle ji plus the minimum between triangle j minus 1 I and triangle j minus 1 I minus 1. I don't know if this works. Now the point is, this works, but we're not taking care of what happens at the sides of the triangle. So at the lateral sides, because of course if I try to sum 7, if I try to sum between 7, between 4 and the non-existing value at the right of 7, it will not work. But first, let's try to return to see if we spot something. So what I want to return is the minimum of like triangle, and then I want of course n, which is the length of the triangle, n minus 1 actually, and that's it. Yes, I want the minimum of the last row. Okay, let's see what we get. Probably an error. Yes, that's what we get exactly. List index out of range. Yes, again, this is exactly the problem I was mentioning before. So, for example, suppose that triangle j plus maybe triangle j minus 1 does not exist. Let's try to see if there is an example of that. So, for example, let's say that we are in the third row. So triangle, so j is gonna be 2 and I is gonna be 2 for the number 7 is equal to the minimum between triangle and triangle 1, 2 do not exist. You see what I mean? So we have to find a way to do that. Okay, we have to find a way to take care of the what's at the sides of the triangle. I'm a bit confused about how to do that though. Maybe I can use any simply if statement. So for example, I can say if I is equal to the length of the triangle j minus 1, then yes, maybe I can do this. Then what I do is to say triangle ji is equal to triangle ji plus, directly I add triangle j minus 1 I minus 1. Instead, if I, maybe actually what I can do is, this is an elif, and what I add is an if. So if I is equal to 0, triangle j, so basically now like we're dealing with the potential 6, so triangle ji is equal to triangle ji plus what? Plus triangle j minus 1 else this. Let's see if this works. There is a syntax error because of course there is no parenthesis in here. Oh wow, it gets accepted. Wow guys, I am very happy with that. Really, I am very surprised that it actually worked, and if it works now I'm gonna be really proud. Wow, that's incredible. It worked. Wow, I didn't expect that. Wow, super happy. Okay, so let's think about the memory and time complexity. So again, we are using the grid that is given to us. So in terms of memory complexity, we are good, very good. In terms of time complexity, again, here we're doing for like j and I. So basically like, okay, like the length of the triangle, it's increasing. So it's difficult for me to now get to the time complexity because of course this increases from 1 to n. So we are literally multiplying like from 1 to, like, let's say this is actually the same length of the triangle, of course. So it goes from 1 to n. So I'm multiplying n by 1, like I'm doing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus n, like until n. So the total is n times n plus 1 divided by 2. So this is O n squared. Yeah, the time complexity is O n squared. So maybe we can improve it a bit. I don't know. The point is, again, maybe there is a trade-off between memory complexity and time complexity. So if we want to decrease the time complexity, we need to store, like, let's say an array ON or something like that. The point is, like, if last time I had a clue about how to do that on ON, now I have really no clue. So here is what I'm going to do. I believe that there is the possibility that this is actually the optimal solution. So I'll check and I'll be back. Okay, bye. Okay guys, it really seems the optimal solution is ON. So fantastic. Really, I'm very happy because I feel that I am getting to understand these dynamic programming problems much better now. So at this point, thank you very much for watching this video, and see you in the next episode.